Alright class, so today we're going to pick up where we left off yesterday. We're going to be moving from writing our skeleton equations of a chemical reaction now to focusing today on how we're going to write our balanced chemical equations. So first off, we think about what a balanced chemical equation is. This idea of it being balanced, all we're saying is that we want to have the same number of atoms of every type of element on both sides of our equation. So the big idea is whatever atoms we have on our reactant side, we also want to have on our product side. And we go about by doing this balancing process by adjusting the coefficients in front of our chemical formulas. So in our chemical formulas, they're going to tell us what the compound or element is made out of. Our coefficients are going to be these small whole numbers that go in front of them in our chemical equation. So one very important thing to keep in mind is that we can only change our coefficients, the number that comes in front of our chemical formula. We can never change the subscripts of our elements or compounds, because what that would result in would be completely changing what that substance is. All right, we can't change H2O to H2O2. Like let's say there's a situation where we need to have additional oxygens. We cannot do this because H2O2, hydrogen peroxide, is a very different substance than waters. So we can't change the subscripts, we can only change our coefficients. So when we are trying to balance a chemical equation, we're trying to do is satisfy one of the most important laws in all of science, the law of conservation of mass. So the law of conservation of mass, something you might have heard before, all it says is a mass can neither be created nor destroyed. So what this means is that whatever molecules we have of each reactant element has to be equal to the number of that molecules of that same type of element in our product side. So what we have is the number of a particular element before has to be equal to the number of that particular element after a chemical reaction. So when we think about what does this mean in terms of conducting a chemical reaction, John Dalton proposed this idea that all chemical reactions was just the rearrangement of a set number of atoms. So you have a particular group of atoms, different compounds bonded with each other, and what we have is that these reactions are really just the breaking and reforming of bonds. So the way that this rearrangement takes place is that we're going to break and then reform the bonds that hold atoms together in a different combination now. So what this might look like is, let's say there's a reactant in which carbon is bonded to hydrogen, and there's an oxygen off by itself. This rearrangement might take place that the bond between the carbon and the hydrogen breaks, and now a new bond between the hydrogen and the oxygen forms in the product side. So a simple plan on how we're going to work through writing these balanced chemical equations is first we're going to want to write the skeleton equation, where all we do is show what reactants combine with each other and what products are going to be formed. From there, we are going to want to adjust the coefficients in front of these chemical formulas of our skeleton equation so that we obey this law of conservation of mass. One thing to think about, our final answer for a balanced chemical equation has to take into account these last two things. First, our coefficients should be the smallest whole numbers possible. So just like when we had an ionic compound where we could reduce or simplify our subscripts, we're going to want to do the same thing as well. Let's say we have 2 of element A is going to react with 4 of element B to produce 2 of element C. What we're going to say is that this is not the smallest whole numbers possible, we can reduce this down, we can simplify it to, we have 1A plus 2B produces 1C. One important thing is that if a coefficient is 1, we actually don't write anything in front of the formula. If we see just the formula itself, it's assumed to be a coefficient 1. So right, this would be our final answer here. We can simplify down what we have in the top line. We can divide 2 by every single reactant product to get this balanced chemical equation here. So there's a number of steps we're going to walk through before we go and start to think about it in terms of real-world examples. So first thing we're going to do for balancing chemical equation is we're going to want to write the word equation for the reaction. So sometimes the question will give you information about what products are produced by what reactants. We want to write this out in a word equation just like what we looked at in the last lesson. Once we have the word equation, we want to figure out what is the correct chemical formula for each of these reactants and products. All right, let's say we write out the word water plus carbon dioxide produces, let's say, oxygen and glucose. Right, we want to write down what exactly is the chemical formula of water, what is the chemical formula of glucose. We want to have that information as well. Based upon what we did in steps 1 and 2, next we're going to want to write out the skeleton equation for this reaction. Again, we always want to put reactants on our left side. We want to put products on our right side. Typically what we'll do, not always, but typically we're going to want to also write the state of each substance in parentheses. And that's what we looked at yesterday, of using either S for solid, L for liquid, G for gas, or AQ in parentheses for an aqueous solution. From there, step 4, and step 4 is probably going to be the most important one. This is going to be the one where you're really going to want to show your work on these problems, is that we want to determine the number of atoms of each element on both sides of our equation. Once we determine the number of atoms of each element on both sides of our equation, we're going to want to balance our coefficients, balance these elements one at a time by adjusting our coefficients. So there's a couple of mini steps we want to follow first. So first thing is we're going to want to balance any elements that are only on each side once. So what that means is that a particular element is only in one reactant, is only in one product. So it only appears in one compound per side of our equation. Once we go through and balance everything that is only in one compound per side, then we're going to move on to the ones that appear in multiple different compounds. So it could be it's in one of our reactants but shows up in 2 of our products. So what we have in this case is typically we're going to want to do any element that is not hydrogen, not oxygen, and that's not an element that's listed by itself. It's just a little bit easier if we take care of the other elements first, and then we can move on to hydrogen, oxygen. And if there's any either reactant or product in which an element is in its elemental form, it's just an element, we're always going to want to do those at the very end. So the one thing to kind of keep in mind with this step of actually balancing the elements by using their coefficients is that it's going to involve a little bit of a guess and check here. So we're going to first adjust one at a time, and by changing the coefficient in front of one chemical formula, that's going to then adjust the remainder of the elements within that compound. So what that means is that if we were to put a 2 in front of, say, carbon dioxide, we're not only adjusting the amount of carbon we have, we're also adjusting the amount of oxygen we have. So last two things we have, and these are more of just kind of ways that we can check our work from what we've done so far. As a last reminder, we always want to double check to make sure our equation obeys the law of conservation of mass. So again, however many atoms we have on the reactant side per element, we want to have the same number on the product side. From there, we also want to double check to make sure that all of the coefficients are going to be in the lowest possible ratio. So in the example we had up here, that we could reduce or simplify down to this lowest ratio. That's what we're going to want to do. We always want to double check to make sure that we cannot reduce our chemical equation anymore. So that would be our very last step. From there, once we work through all 70 of these, we would have our final answer for our balanced chemical equation for that particular reaction. So what we're going to do right now is walk through a couple of examples. The first one is actually looking at the second example we did in yesterday's class. So what we do is we're producing liquid water from hydrogen gas and oxygen gas. So again, if we think back to our word equation, what this means is that we have hydrogen is going to react with oxygen, and this is going to produce water. So we think about our reactants, and we want to think about their chemical formulas here. We have hydrogen, which is H2, and it's a gas. And we're going to have oxygen, which is O2, and it's a gas. On our product side, we're going to have water, which is H2O. Again, we're told it's going to be liquid water. So one thing right here, so this information right here, this will be given to us in our problem. So for the problem set that you guys are going to be doing on Friday for classwork, this information of what the chemical formulas are going to be given to you in the problem. So now what we want to do is we want to rewrite this word equation, but in terms of the chemical formulas, this is going to make up our skeleton equation. So we're going to have hydrogen gas, H2 small g, plus oxygen gas. It's going to produce, or it's going to yield, liquid water. So right now we have done steps 1 through 3 here. We've written our skeleton equation, and now what we want to do, and what you're going to need to show in your homework, is this very important step in number 4, determining the number of atoms of each element on both sides. So the work we want to see will be something like this. So we know that on our reactant side, we have hydrogen and oxygen are going to be our 2 elements here. And we can count based upon the subscript. We know that hydrogen is going to have 2 atoms. Oxygen is also going to have 2 atoms on the reactant side. If we look over to the product side, we look at hydrogen. We're going to have 2 hydrogens, but we're only going to have 1 oxygen. So right now, what we have is the fact that our 2 oxygens on the reactant side does not equal our 1 oxygen on the product side. This tells us that we're currently unbalanced. So what we're going to want to do is adjust our coefficients so that we have a balanced chemical equation. So we still know the reactants and the products are going to be the same. Still going to have H2 as a gas. So we're going to have it combined with oxygen as a gas. We're still going to produce liquid water. But what we want to do is adjust our coefficients so that what we have is completely balanced, same number of reactants as we have products. So the first thing I'm going to do is I know that this oxygen currently is unbalanced. We have 2 to begin with, but only 1 to end with. So what I'm going to do is I need to make sure that there are 2 oxygens in our products. So I'm going to write in a 2 coefficient in front of my H2O. What this now means is that we go from 1 oxygen up to 2. But we also have to adjust our hydrogen now on our product side. So a coefficient of 2. So that means we have 2 water molecules. If each water molecule has 2 hydrogens in it, what this means is that we're going to have 2 times 2, or now a total of 4 hydrogens. So now what we have is oxygens are balanced, but now our hydrogens are no longer balanced, right? If we want to compare this 2 to this 4, these are now going to be unbalanced. So if I end up with 4 hydrogens in my products, I'm going to have 4 hydrogens in my reactants. So I'm going to put a coefficient of 2 in front of our hydrogen. We now have 2 times 2, or a total of 4 of our hydrogens in the reactant side. So now when I go through and compare, right, we look at 4 hydrogens in the reactant side, 4 hydrogens in the product side. So they're balanced, so that's good. We look at the reactant side, we have 2 oxygen atoms. And the product side, we're going to have 2 oxygen atoms as well. So they're balanced as well. So what we have is all of our reactants are balanced with all of our products. So we're going to have our final answer for our balanced chemical equation here. So what we're going to do is one more example here to finish off today's video. It's going to be a little bit more challenging. It's going to be an example of a chemical reaction we have not used so far as an example. What we have is we have diborane gas. It's going to react with liquid water to produce boric acid and hydrogen gas. And they tell us information that boric acid is going to be an aqueous solution. So first off, our word equation, when we think about what's reacting with what our products are, we have diborane is going to react with water. And we know that it's going to produce boric acid and hydrogen gas. So we're thinking about the chemical formulas of each of these. Again, this is information that is going to be given to us in the problem itself. But in this case, diborane gas is going to be B2H6. Here we're told it's a gas. We have liquid water, so H2O. It's going to be a liquid. And guys, just one quick apology. One thing I'm realizing, if we scroll back up the top here, again, remember we want to include our states of matter for each of these. Sorry, that one last point we did not want to talk about at the very end there, but we always want to have their states of matter if it's given to us in our problem, or unless specifically told not to use them. So again, now we've taken care of our reactants. We're now going to look at our products. And if this was a homework question, you would have been given the fact that boric acid is H3BO3. And hydrogen gas is going to be, last thing is that we know that boric acid is an aqueous solution. And the very last product we have is hydrogen. We know hydrogen gas is going to be H2. Again, it's a gas. So our skeleton equation is we're going to have B2H6, which is a gas. It's going to be reacting with H2O, which is a liquid, and that's going to produce H3, BO3, which is an aqueous solution, plus H2 as a gas. So again, we've worked through steps 1 through 3. Step number 4 that you must show on your homework to receive credit is going to be counting up the number of atoms of each element. So we're going to have boron, our reactant side, if we count up, we're going to have a total of 2. And so we're going to look at hydrogen. We're going to have 6 from boron, plus an additional 2 from water. So that's going to give us an initial total amount of 8 hydrogen atoms. Last thing is we have oxygen, and we're going to have just 1 of them from water. When we look at same elements on our product side, boron, we see we only have 1 of them. For hydrogen, we are going to have 3 from our boric acid, 2 from our hydrogen. So it's going to give us a total of 5 hydrogens. And then again, when we look at oxygen, we're going to have 3 of them. So right now we're looking at our reactant side and our product side. None of them are balanced. So what we have here is going to be an unbalanced skeleton equation. So out of these 3, we want to figure out which one we want to deal with first. So we scroll all the way up to the top. Here our rules is that we want to balance elements that are only on each side first. And again, we're going to want to wait to do hydrogen, oxygen, and any free elements are by themselves. So when I look through this, I see that we have hydrogen and oxygen. If we can, we're going to want to wait on them. But we know that boron right now only appears in 1, and we currently are unbalanced. So first one I'm going to want to balance is boron. The fact that we start out with 2 in the reactants, but we only have 1 in the product side. So when we go to write our balanced chemical equation, B2H6 is a gas that's going to combine with H2O as a liquid. It's going to produce our boric acid, which is H3, BO3, which is an aqueous solution, as well as hydrogen gas. So we want to, if we start with 2 atoms of boron and we want to end up with 2, means we have to change and put now a coefficient of 2 in front of our products here. Because what this does is, remember, we can almost think of it as like the distributive property. It's going to apply to our hydrogen, to our boron, and to our oxygen. So we're now going to have a total of 2 borons, which is what we want. So it's now going to be balanced with our boron and the reactants. What we now have is 2 times 3 is going to give us 6 hydrogens just from our boric acid. We also have to take those 6 acids, hydrogens, and combine with that 2 we have in our H2 gas. So from here we're going to have 6. From here we're going to have 2. So we have 6 plus 2, which is going to be 8 total hydrogen atoms. Last thing is we have 2 times our 3 oxygens that are each boric acid molecule is going to give us a total of 6 atoms of oxygen. So right now we're looking at it, we have 2 borons on both sides, which is good. 2 hydrogens on both sides, which is good. But our oxygen is in balance. We're going to need to add in another step here. Put this one in purple. So in order for us to end up with 6 oxygens, we have to begin with 6 oxygens. So when we look at the left side here, we're going to have to put a 6 in front of our water here. So that way we can go up to 6 atoms of oxygen. But again, because we're putting a 6 in front of H2O, we think of it as being kind of distributed over everything. So that means it's going to also adjust the amount of hydrogens we have. So from right here, we're going to have 6 times 2, or 12 atoms of hydrogen. And then from here, we're going to have 6 as well from our diborane. So our new total amount for hydrogen is going to be 12 from the water, plus the 6 we have from the diborane, going to give us 18 atoms of hydrogen. So now we have boron is balanced, oxygen is balanced, but now our hydrogen is no longer balanced. And this is why we always want to adjust the ones that are elements just by themselves last. They're the easiest to manipulate. So if we go in blue here, we know we need to get up to 18. So our goal is to have 18 hydrogen atoms. And if I'm looking at what we have written so far, is that this boric acid has 2 times 3, a total of 6. So we've already taken care of 6 hydrogen atoms. That means we have 12 hydrogen atoms left we want to account for. So if we know that each molecule of hydrogen contains 2 atoms of hydrogen, we're going to need a coefficient of 6 here to give us our 6 times 2, or 12. So think about all the hydrogen we have from hydrogen gas. We have 6 times 2, or 12. If we look back to our boric acid, we have 2 times 3 hydrogens, gives us 6. Right, so this gives us the 18 we want. So now we are looking at comparing our reactant side to our product side. We're going to have 2 borons on the reactants with 2 borons in the products. We have 18 atoms of hydrogen in the reactants, 18 atoms of hydrogen in the products, 6 atoms of oxygen in the reactants, 6 atoms of oxygen in the products. So we have is everything balanced. This is our final balanced chemical equation with a coefficient of 1, a coefficient of 6, coefficient of 2, coefficient of 6. So I can't simplify this at all. 1, 6, 2, 6. There isn't any lower common denominator here. There's nothing we could factor out. So our final answer is going to be what we have down below here. I'm going to highlight in, or put a box around in black. And then one thing that we are going to absolutely need to see in our homework is we do want to see these steps that I'm going to circle here written out. So if you do not do these steps of showing how you're able to balance your chemical equations, you will not receive credit for tonight's homework. Sorry, for classwork tomorrow. Again, there's going to be no homework for tonight, but tomorrow you will have a problem set posted for classwork.